Yeah, okay, thank you. So in this talk, what I shall do is talk to you about telescopes of different types, and then also try and tell you how, what are the kind of telescopes that we particularly need for solar system objects, okay? And why we need, first of all, the telescopes, and what are the special things about, okay? So if you take a normal camera and put it on a stand outside in the night sky, and you take a long exposure image or a photograph with a long integration time of a few hours, this is the kind of pattern that you can see. You will see the trails of the stars in the night sky. So each of them is the track recorded by a star as the Earth rotates on its axis. Okay, with the pole star being sitting right here, just at about 1 degree away from the true North Pole. So this is what happens if you have if you have a wide field camera sitting on a mount stationary on the surface of the Earth. So in the case of telescopes, we need to go the other direction. We need to rotate the telescope in the direction opposite to that of the Earth's rotation, so that we can track the object, celestial object, as it moves from east to west. Okay. So that's the typical thing. What I will do in this talk is I will try and give you some glimpses about what are the different types of telescopes, and also I will try and cover some of the points which in fact, there's only one which really differentiates solar system observations versus the rest of astronomy. Okay, we'll come to that in the next few minutes. Typically, when you consider what kind of telescopes are there, we can subdivide them by wavelength. So starting from radio right up to X-rays and even gamma rays, we can observe using telescopes of different types. The only things that vary are the manner in which you collect the photons and the detectors that you use for sensing these wave bands. Okay, and you can also define them in terms of the light collecting element, whether it's a reflecting type of telescope or a refracting type of telescope. For example, at optical wavelengths, if you make the telescopes using lenses, which is what people used in the initial days, then they are called the refracting type or the refractor. Okay, and the largest is about 40 inch across, 40 inches of pure glass. The trouble with this kind of glass-based telescopes is that you cannot support a glass lens in the center. So gravity becomes the defining element in defining the shape of the glass surface of the lens. And it's not very easy to have a good quality image at the focal plane finally. On the other hand, with reflecting telescopes where you use mirrors, it is relatively easier to build larger and larger telescopes. For example, the largest currently operating ones are around 10-meter diameter, made of multiple segments. Okay, and the advantage there is that you can support them at the back of the mirror, and you can also define the shape of the mirror in an active manner. So you can compensate for variations in real time. Okay, I'll talk a little bit about that subsequently. These are telescopes where you make use of techniques called adaptive optics. Okay, so now let's look at what are the wavelengths of electromagnetic radiation that come from celestial bodies. Okay, so from the universe, from any of the objects in the universe, you can expect wavelengths of the electromagnetic spectrum right from radio, which comes to about a few thousand kilometers of wavelength, right down to gamma rays, where the wavelength is much smaller than an atom, 10 power minus 12 meter. Okay, and in this slide we have the details about the wavelength and then the typical scale of the objects that you can see at those scales. Okay, it also tells you what are the frequencies that would be associated with the corresponding wavelengths, and also, of course, as a black body spectrum, what is the kind of temperature where that particular wavelength would peak. Okay, for example, in visible light, the solar sunlight, for example, peaks at around um, yellow-green color, which is around 6,000 degree Kelvin. So this is typically the kind of electromagnetic spectrum that one can see from the stars and from other objects in the night sky or in the sky basically. And what you get from each waveband is something quite different compared to. So in order to have a holistic information about the entire universe, you need to study it at all possible wavelengths that you can have access to. Which brings me to the next question of how many of these are actually observable from the ground. Okay, so for example, this is, I think you might have already seen this by other speakers in this series, but just for the sake of completeness, let me go through it. Thankfully, the gamma rays, X-rays, and UV light are completely blocked by the upper atmosphere of the Earth, and thanks to the blanketing by the upper atmosphere, we are protected from these harmful radiations. What does get through to the bottom of the Earth surface is some amount of visible light, and there is a little bit of infrared up to about with small windows in in the near and mid infrared up to about 30 micron. Okay. Beyond that, again, it is completely absorbed, and you need to go to space in order to observe most of the infrared spectrum, including in the millimeter and sub-millimeter. There are few windows here. You can try and get some observations. It's not completely flat, completely absorbed at this point, but you do get some windows here, which allows some kind of telescopes, which I'll talk about in a moment, to observe these from high altitudes on the Earth's surface. Okay, so from something like 5,000 meters, you can have access to some of these windows. This is a plot as seen from the ground at sea level, okay, from the Earth's surface at sea level. Radio waves are essentially travel down to the surface of the Earth, and one can actually observe the universe in these bands relatively easily. However, even here, beyond a few tens of meters, the wavelength is completely blocked. Okay? So we don't have any major ways to observe the universe at longer wavelength frequency, or longer wavelengths than these. Now let me come to what kind of telescopes we have in the optical in this electromagnetic spectrum. We'll start with something which we should be really proud of, and that is the giant meter wave radio telescope, which is at these frequencies or at these meter wavelengths. It is the largest one in the world. Okay, it is near Pune, Kolad, near Pune in Maharashtra. And it consists of 30 dish antenna or a parabolic antenna of 45 meter diameter each. Okay, and you can judge the size of these mammoth dishes by looking at this small vehicle here in front of one of the antenna. So these parabolic antenna can be steered to any direction. And what happens is when the radiation comes down from the sky, it gets reflected from a series of wires which are essentially transparent at other frequencies, but at a wavelength of a meter wave, they form almost smooth dish along the surface of this antenna, and they reflect the photons collected or the wavelengths to receivers which are sitting at the focal plane of this GMRT. Okay, and then the light is combined from there and fed through several kilometers of fibers and optics, fibers and channels, and one makes use of very complicated mathematical models to retrieve the images at radio wavelengths from this kind of a telescope. So this is one of the kind in the world, and India is now partner to a larger telescope which is being built in South Africa as well as in Australia jointly, and India will also be a partner of it. It's called the Square Kilometer Array, where we have interesting results expected in the future. Now, coming down in terms of wavelength to shorter wavelengths, we have the IRM observatory, for example. I'm just picking and choosing just a few telescopes from around the world just to give you a flavor. There are many observatories and many antenna of this kind, except, of course, the GMRT, which is kind of almost unique, you might say. You have the IRM observatory, which is a single dish of 30 meter size, and you can judge the scale of this thing by my figure standing here. Okay, so it's about 30 meter across in this dimension, and it is also fully steerable and can observe at millimeter wavelengths. So at millimeter wavelengths, what are the advantages is that you can observe a lot of large molecular transitions. Okay, so I think some of these things we covered during my previous talk, so we'll not go into it in more detail, but we can have questions if people are interested. The other development which has happened in recent times, IRM is an old telescope, but in recent times we have had the another telescope called the Atacama Large Millimeter Array. Okay, so this instrument works from about 0.32 micron, 0.32 millimeter to about 3 millimeter. Okay, and it has 66 dish antennae of various sizes. It's essentially a 12 meter kind of antenna, dish antenna, and 66 of them laid across the plateau of Atacama in Chile in South America. It's it's at an altitude of 5,000 meters above sea level, and it's almost next to impossible to work there in real time. So one is not allowed to stay there at the top of the plateau for very long duration. All of the work is done remotely, of course, and we have a computer control to receive the data from this kind of a dish. So the light is again reflected back from here into the receiver, which is sitting at the top, and the receiver would have different kind of sensors, bolometric cameras and bolometric arrays, which allow you to retrieve images of the night sky in the millimeter, sub-millimeter wavelengths. Again, this has a very important role in terms of molecular emission detection, and nearly 140 molecules of various complexities have been seen in the interstellar medium and in various objects of the universe, and this ALMA is to be thanked for that. Let's now look at what is the advantage of going to space for the other kind of telescopes. Essentially, of course, the first point is that you have access to wavelengths that don't reach the ground. And the second is that, for example, at optical wavelengths, the moment you go outside the Earth's atmosphere, you are outside of the effects of the Earth's atmosphere. For example, the night sky, if you go out on a typical night in the middle of a city, you will find that it is there's a lot of twinkling happening in the night sky. Okay, the stars appear to twinkle. But the moment you go to higher and higher altitudes, the amount of atmosphere goes down, and then the sky starts becoming more and more stable. And the moment you go into space, there is no turbulence at all near the telescope. So you essentially end up having a wonderful diffraction limited image from the instrument. So what are the telescopes and observatories which are working in this direction? I will highlight only a couple of telescopes of recent times, but not the very newest JWST. One reason being that it is interesting to see what kind of science was possible with these bands, which, for example, the Herschel Space Observatory. This was a telescope of 3.5 meter size, this part here, and it's completely shielded from one direction, and then you can point to any part of the sky. And it was made essentially for far infrared and sub-millimeter observations. All of the entire telescope was cooled using liquid helium, and also the suite of instruments, which were essentially photometers and spectrometers. and imagers, of course, working in at the focal plane of this 3.5 meter dish, where the light was guided from the primary to the secondary and through a hole in the primary into the later part where you have the cryogenic tank and all the suite of instruments there. So fantastic set of results from this observatory for all kinds of objects. And in case of solar system science, it was the peak was to get information on the sizes and albedos of minor bodies in the solar system. So this was an important mission in that sense. Other missions of this kind which have been very useful are the WISE and NEOWISE missions. And I hope that those of you who are interested will go and look at those missions also separately. Coming down in wavelength to more closer to optical, this one is the Spitzer Space Observatory. You can get a glimpse of the size by looking at this technician working on the solar panel of this observatory prior to launch. This was also a cryo-cooled observatory with a large mirror and cooled imagers, spectrographs, and so this is the instrument which made a lot of images of the night sky at near to mid-infrared wavelengths, and there are some fantastic images if you go and look up the glimpse survey of the Milky Way, for example. Okay. There have been, of course, some measurements and spectra of, in the mid-infrared using this observatory for comets as well. And they found that there is a large similarity between the cometary spectra and the spectra of young stellar objects. In fact, the first of those results was from the Infrared Space Observatory, which was launched by the European Space Agency. Okay, and so they were the ones who first showed that the comets had material which were very similar to what we see in young stellar systems today, where stars are just forming. So that gives you further direct proof that studying the comets is like studying the young stars that are being created. Okay, so it's a record of the history of our solar system as well. So that brings me down back to the Hubble Space Telescope, which is of course quite famous. I think all of you would have heard about it. This is still very active and still providing us with a lot of very exciting results. I'll just show you two images which show you why going out of the Earth's atmosphere has made a fantastic contribution. This telescope has detectors and instruments working in the optical and UV, as well as in the infrared, and they had several generations of instruments through the possibility of changeovers by the astronauts on the space shuttle. So a couple of examples from this observatory are the color mosaic of Saturn here and Jupiter on the right. Saturn's polar aurorae are seen in this false color composite, where the STIS UV images and data were combined with the ACS visible light to show you the auroral emissions in the Saturn's polar regions. Okay, and similarly, this is a very high resolution imaging of Jupiter's surface immediately after the comet Shoemaker-Levy 9 had impacted. Okay, there were 20 fragments which hit Jupiter one by one, and although they were all hitting Jupiter on the other side of the Jupiter when they hit the comet, hit the planet, but when the field rotated into the field of view of Earth, that is when these images were recorded. Okay, so they are several hours after the first impact, and but still you can see very well how this developed further. So as I said, you can launch telescopes to space, but at optical wavelengths you want to avoid turbulence. That's why you want to send them to space. Okay, but you can also do the other way. You can study the Earth's atmosphere and how it is varying over a short period of time, and build optics in such a way, it's called adaptive optics, such that you can compensate for the turbulence in the Earth's atmosphere in almost near real time. Okay, and by doing that, you can go for larger and larger telescopes. Why do you want to go for larger and larger telescopes? Simply because larger telescopes means better resolution, and you can also get more photons, which means that you can have much better instruments and much more high signal to noise ratio measurements of spectra or images or whatever you are wanting to observe. So this is one of the techniques, the adaptive optics and active optics, which allows you to compensate for the Earth's atmospheric turbulence, what we call seeing in technical terms, and as twinkling in the layperson's language. So examples of such telescopes are many. And I just show you one example here. This is the European Southern Observatory's very large telescope, an array of 4 8-meter class telescopes, which are sitting here. And they also have smaller telescopes sitting along with them. And this is a close-up view of that. Light from all these 4 are combined subsequently in order to get interferometry. But you can also individually observe each telescope can observe individually different targets, and you can use them as a conventional telescope also. The latest observatory which people are planning and building right now, and which will be coming online in the next 1 or 2 years, is the Vera Rubin Observatory, also called earlier the LSST, Large Synodic Survey Telescope. This is a fantastic piece of instrumentation, and it is coming up again in the desert of Chile, not very far from the VLT and Alma site. And it is based in the desert, of course, and at high altitude. And the design is quite interesting. It is having 3 mirrors. Okay, you have the outer mirror, outermost mirror. So this is the parcel of light, primary mirror M1, which is 8.4 meters across. Okay, and this light then gets reflected to the second mirror here, which is called M2, and this is a mirror which is 3.4 meters across. Okay, and from there the light gets further reflected to the central part of the M1, which has a different kind of shape, okay, a different configuration. And so this is one piece of glass, but 2 different shapes on the same surface. And then from there, it goes through a series of corrector plates, which are shown here, and falls on a camera, which is the largest ever made camera in India, in the world. It's the camera itself is 64 centimeters across. Okay, so the detector plane is 64 centimeters across. The filters in front of it, which decide what wavelength you are observing at, is 76 centimeters across, and that's bigger than some of the other bigger refractors which were made. And then you also have a corrector plate L2 and then an L1. And the L1 corrector plate is 1.55 meters, which is almost as tall as a human being, right? So that's the largest ever lens built for astronomy or for any other purpose on ground. So all of this provides you with diffraction limited, not exactly diffraction limited, but seeing limited images right down to 1.75 degrees from the center of the field of view. So you have a 3.5 degree diameter field of view of this with this telescope. So at a time you can image 3.5 degrees of the sky. So what does that tell you in terms of science? It means that it's going to be able to survey all kinds of objects which vary, and you are going to be able to cover the entire night sky within 2 or 3 nights. Okay, and which means that on any given night you should be able to track more than 5,000 asteroids or near Earth objects or trans-Neptunian objects or comets or whatever you like. Okay, which show their presence by moving across the field of view as a trail. So this is going to really revolutionize our understanding by really extending by manifold the catalog of solar system objects. And we're looking forward to getting the results from these from this observatory to follow up and study all the new objects it's going to find in the very near future. We expect it to become online, I think, in the next couple of months to a year or so. Now let us look at some of the Indian optical and infrared observatories. It's not a complete listing by any means. I just picked and chose some examples just as a flavor of what is going on in the country. And let me start with what used to be the largest telescope built in India. And I guess built in India, it's still the largest. It's the 2.34 meter VBT Vainu telescope in Kavalur, which is not far from Bangalore. And it's operated by the Indian Institute of Astrophysics. It is it's on a horseshoe mount. The 2.34 meter mirror is sitting here in this chamber, and it can be pointed to any part of the sky by rotating it on this axis as well as on this axis. And this axis is supported on one end by this horseshoe shape cradle, which allows uniquely this telescope to point even at the North Pole, which is not always very feasible in other telescopes of the equatorial mount kind. So this telescope has one drawback in that it is sitting in a region where there is a lot of cloud cover, and very frequently the sky is bad. But along with this telescope and other telescopes on the campus, they have a formidable set of observing equipment at a short distance from Bangalore. And a lot of very interesting results have come out from here. I don't have time to go into results simply because we were to talk about telescopes here. We can discuss results. If people are interested, you can drop me a line or something and we'll discuss it further. Give you another example. I then went all the way from next to Bangalore to the other extreme and went to Hanle in the Ladakh region, where they set up the 2-meter Himalayan Chandra telescope. There's also a wonderful telescope, and it's completely remotely controlled from Bangalore. You do have local people who are on the site to make sure that things are running properly. And it has a whole suite of instruments ranging from images to spectrographs, both optical and in the infrared window. Several instruments are mounted at a time on the telescope, and one can select them through software at short notice. Okay. Now, there is another very interesting telescope which has been built. It is the largest telescope in India at optical wavelengths, in fact. And this is the 4-meter International Liquid Mirror Telescope. So the concept is quite interesting. You have a single mirror, which is made up of accurate surface, but then it has, instead of glass, it has mercury sitting at the center. And when the mirror is rotating at reasonable speed, the mercury spreads across, providing you with a very accurate surface definition, which allows you to build a 4-meter mirror at the fraction of a cost of what a real 4-meter telescope would cost. And the only problem with this kind of a telescope is that you have to point at only the vertical sky, and whatever sky is passing overhead, you can observe it. Okay, so the telescope has several filters, and it's possible to take images in a continuous span. As the sky rotates overhead, the telescope reads out the images, and then it is stored as long strips. I'll show you one example of, so this is the observatory from outside. You have the control room here, and then the compressor room and other auxiliary building. Because mercury is a poisonous thing, you're not allowed to go in once it is in operation. And in fact, even during operation, when it is not in operation, only authorized people are allowed access, only those who really need to be in the building. Okay. So, example of an image from this telescope is this image which I took from the IIRS website. These are among the first images from the ILMT obtained in October 22. And it shows, in fact, one of the asteroids as it was tracked across the field of view of the instrument. The blue track here is from a space debris which is much nearer to us, and because of that made a continuous track in one of the images of this false color composite constituted from multiple images at different bands at different wavelengths in different days. Okay, so that is how the asteroid looks different color on different days, and it shows over here. So these were done at in 3 different bands and then color composited as a false color to bring it out. So the asteroid itself does not move as much, but if you were to combine it as a single long exposure, you would get a trail similar to what this near Earth object has shown on this space debris, which probably was within the Earth-Moon system, maybe somewhere nearby, near Earth satellite, maybe. And that's how it has moved across the entire field in a single exposure. So now I come to the observatories operated by PRL, and I'll conclude very quickly. We're running short of time probably. This is the 1.2 meter, one of the oldest infrared telescopes in India. And we have also here the 43 centimeter telescope inside this small dome, and a 50 centimeter telescope on this peak here, which is just a little small walk from the base to the top. And then now we have the 2.5 meter telescope, which is the largest telescope in this part of the country. It's installed recently and started producing some interesting, very exciting science results. And I'll just show you one. Let me show you photos of each of the telescopes. So this is what the telescope looks like from inside this dome. The dome itself is painted dark black, dark color in the inside, so that it won't reflect any unnecessary light from scattered light from outside. You have the telescope mounted in an equatorial mount, fork mount. So, and here we have the instrument at the focal plane of the telescope. This is the primary mirror. You have a second mirror here called a secondary, and then the light from the primary is reflected by the secondary through a hole in the primary to the focal plane instruments. The focal plane instruments can be changed, and we can have a suite of instruments. Many of them were built in-house at PRL, including several polarimeters and infrared cameras and spectrographs. So this is the first one in the country, and recently we have installed a second one, which is in operation. And new instruments are always being defined and built for this telescope by people at PRL. On the 2.5 meter also we have spectrographs built at PRL. In fact, I should have mentioned that on the 1.2 meter we have a very high resolution spectrograph called PARAS, which discovered the first exoplanet seen from Indian soil. And similarly with the 2.5 meter also we have a high resolution optical spectrograph, which provides very interesting results already. So this is the 2.5 meter telescope, and at the focal plane we have a possibility of mounting 3 instruments, one on the main port and 2 on 2 side ports. We have the 50 centimeter in this kind of a dome here at the top of the peak, and this is what the view looks like from standing from outside and through a kind of transparent dome idea. It's a trick photograph actually. And then this 2.5 already shown you. This is a 43 centimeter in a fully collapsible dome. And the advantage of this is that this kind of a setup is that you can quickly move to any part of the sky in order to look at transient objects at short notice. Okay, so you're not limited by the time that the dome takes to rotate in front of the telescope. The telescope itself can move to any part of the sky in very short notice. We also have an all-sky camera at Mount Abu, and you can see the night sky very nicely. In fact, even the Milky Way at times. But it's also good for fireballs and meteor imaging. And one example is this spectacular image of fireball as it entered the Earth's atmosphere one morning, one early morning. This was just before sunrise, well before sunrise, of course, around 4 in the morning, I think. And the entire control room, I was there at the observatory at that time, and then the entire room was filled up with a kind of green light. And when we looked at the image in the all-skies camera, we were able to see this light. It was a very exciting time to be at the control room at that time. So what are the different requirements for solar system science? Because, telescopes wise, the same telescopes that we use for the rest of astronomy, we can make use of for solar system objects also. The main thing is to do with tracking. Okay, solar system objects are nearer to us, and just that's the way you see the nearer trees when you're moving in a train. You see the nearer trees moving faster than the background trees, which appear almost stationary. So the same thing happens here. You see a parallax, and you see the foreground solar system objects moving across the field of view very fast, okay, relatively. So then what we need to do is we need to track the object using what we call non-sidereal rate tracking, which means that you are using tracking rates which are as per the object, not as per the stars. Normally, if you were to take images of the stars, you would then be compensating for the rotation of the Earth's axis. Now, on top of that, you need to also, I hope that you can see this video. It is supposed to show a bright spot at this location, which is the asteroid. It's a near-Earth asteroid called 2004 BL86, which we observed as it flew past very close to the Earth, just 2 times or 3 times the Earth-Moon distance. So it came extremely close to the Earth. Normally, it's just a few hundred meters across and extremely faint. But on this particular night, it brightened up to be one of the brightest of asteroids visible in the night sky. And all these objects which you see passing it are the nearby stars, are the background stars. And the telescope had to really race across the sky to track this asteroid as it moved several degrees in an hour. So the instruments which are at the focus of the telescope decide what kind of science that you would like to do. So we are deciding the instruments based on what are our scientific aims. So we go with spectroscopy, imaging, and polarimetry. I will just briefly tell you something about spectroscopy because that's something of interest, I think, for many people. This is one of the instruments on the 50 centimeter as well as it has been used on the 1.2 meter. This is showing it on the 50 centimeter. This is on the 1.2 meter. And it has a spectral resolution of 1000 with a wavelength coverage from 380 to 780 nanometers. And this is what the instrument looks like mounted on the 1.2 meter. So this mirror is 1.2 meters across. So the optical path looks like this. At the focal plane of the telescope, you have a slit, and the light that you don't want to pass through to the slit is reflected to another mirror here and passed into what we call the guiding camera, that is this blue camera. And the red one goes through the spectrograph, gets reflected from this mirror, goes through a collimator lens, is incident on the grating as a parallel beam, then passes through another focusing objective lens, and then falls on the spectrograph acquisition CCD or camera, that is this red CCD. So this camera has been used extensively for over 24 comets in the last 6 to 8 years. And this is the advantage that because this has this guiding camera, you can actually see the object as it moves across the field of view. You can, of course, move the telescope to compensate for this movement, but there will always be some minor residual movement, which allows, and this kind of a guide camera allows you to build up the signal. So the guide camera has exposures of 5 to 10 seconds, whereas on the acquisition camera, where you have split the light into a spectrum, you need an exposure of merely 1 hour. Okay, so in order to build up the signal, you need to make sure that you are tracking the comet accurately. So that is done by imaging the camera, the comet as it as the telescope follows it. Okay, so if needed, then you can make corrections. And this is the kind of spectrum that you can generate from this. I covered this a little briefly, but since there was a question in the previous talk, just to tell you that there are some very specific signatures of different molecular species, and these are pretty unique. And so it is relatively easy to distinguish at a coarse level what are the kind of molecules present in the coma of the comet. We'll go into more details if someone has an interest. So summary is that telescopes are rarely used by astronomers to see the objects by eye. So this is something which people see in the movies, and also, of course, you have heard about how Galileo discovered the moons of Jupiter by looking at Jupiter through his self-made telescope. But nowadays we rarely do that. We actually build instruments and put them on the focal plane of the telescope, and the telescope has the only job of collecting light from the distant heavenly bodies and putting it into our instruments. So I think I'll stop with that and take questions.